Let's calculate the probability for something called independent events. We're going to go ahead and use this table, this sample space here of values, and what these represent are all the different possible cards that you can pull out of a deck of cards. I'd like for you to copy this table down in your notes with hearts and diamonds and clubs and spades, and I'll give you some background info on what these things are called. These four things right here, they're known as suits. And it's important that you know that in a standard deck of cards, and that's what this is a standard deck, there are no jokers, not in a standard deck. You may get jokers with your cards, but you got to take them out to have a standard deck. And in a standard deck, you get four suits, and they are hearts, diamonds, clubs, and spades. Of the four suits, two of them are red. That means half the cards are red, and two of them are black. That means the other half are black. The other thing is that for each suit, like for hearts, there will be 13 cards. One way to refer to them is ranks. We would say that there is 13 ranks. And that's these guys right there. And then the other thing is let's see. So if you pick any particular rank, like let's say we pick the rank of 7, there would be 4 of those. What gets a little trickier is there's this concept called face cards. And that's these guys right there, jacks, queens, and kings. Now aces look a little different, but they're not considered face cards. So there's just this many face cards in a deck. So if you can write this down and add it to your notes, you will be able to answer questions regarding cards. Now let's do some math. Probability for independent events. Let's say we wanted to find the probability that we draw 2 cards. We'll draw 2 cards from a standard deck, and when we do, we want to know the probability that we get a 7 and a jack. So here's 7s and here's jacks, and we just want to know what's that probability. The way we'd calculate it is we'll use the sample space. We'll say to ourselves, well, in our sample space we can see that there are 4 7s, and how many total cards? I'll let you pause the video for a second and count for yourself, and then I'll tell you in a second. Okay, hopefully you counted, and so what you should have come up with is 52 cards. And since there's 4 that are 7s, and there's 52 total cards, the probability of picking a 7 is 4. Oops. Let's go ahead and make this. How about this? We'll say 4 out of 52. So that's how many 7s. And then there's also the probability we're also wondering about picking a jack. And again, for jacks, there's 4 of them out of 52 cards. Oh, wait a second. This brings up a really interesting point. When I picked the 7 out, did I keep it out or did I return it to the deck? This is a concept that is known as with or without replacement. For independent events, we're going to assume that it is with replacement. Or better yet, I'll say if you're assuming with replacement, or if you're told that you will be replacing the cards, then you will definitely have independent events. Because if we take a card out, 7 or not, and put it back, the deck is going to stay exactly the same. If we take a card out, then our next card, there's not going to be 52 to choose from. But if we take the card and we put it back into the deck, then we will, when we go to choose the next card, we'll still have 52 cards to choose from. So probability of getting a 7, 4 out of 52. Probability of getting a jack after we replace the card, and we are going to replace the card, it will be it'll be 4 out of 52. And you know, I could have written this in another way. You guys, some of you I know will want to reduce your fractions right away. I recommend that you don't. I recommend you leave your fractions like this to start with so that you can backtrack and figure out how you got the fraction when you're looking through and studying your notes. So let's continue. These guys can now be reduced. 4 over 52 is the same as 1 over 13 and 1 over 13. And when we multiply those together, we get 1 over 169. And I'll remind you that we can write probability as a fraction, or as a decimal, or as a percent. So let's try that. All right, so we'll take 1 and divide by 169. There we go. Equals. It looks like it's going to be about 0.6% or 0.006 or 0.6%. So we can rewrite this as approximately 0.006, which is also the same as 0.6%. And on a test, you might have to write out the probability in one of these three ways. I'm not going to say it's always going to be one way. I will let you know which way for a particular question. Anyways, if we have a situation where we're told we're going to replace something after we take it out, then we will have independent events. If you are not told whether or not you are going to replace, then you can assume that you will not replace. So that'll be the next example that I'll show you. But before I show you the next example, I'd like to generalize. Now that we've discussed the idea that if we have the probability of something and the probability of something else, that we multiply together the two probabilities, I'd like to generalize and make a rule that you can write down. We'll say if we want to know the probability of A or event A occurring and the probability of event B occurring, the way we figure that out is we do probability of A times the probability of B. Or at least that's what we do if we have independent events. We'll take a look at another example where the events are dependent. Anyways, this is the rule, and you should write it down.